Okay, so we want to now look at the concept of a perpendicular bisector of a line segment. So let's start off with a definition. So let's take a line segment. Let's label one endpoint 1A, one endpoint B. And let's take the midpoint. Let's label that M, shall we? So the perpendicular bisector is the straight line which cuts this line segment in half, and it crosses at exactly 90 degrees. Okay, so it's cutting in half, and it's a right angle on both sides. So this is called, unsurprisingly, the perpendicular bisector of the line segment AB. Okay, so just a few things to point out. First of all, AM is equal to MB. Very good, it's cutting it in half, it's a bisector. Perpendicular, it's going at right angles. So let's label this line SAB. And we have SAB is perpendicular to the line segment AB. Okay, so we're going to study these in quite a lot of depth today, and we're going to see how they can be used to prove lots of kind of interesting things about triangles. So let's start off with an example, shall we? Okay, so given an isosceles triangle, so let me just draw it here. An isosceles triangle of the following form. So I attempted an isosceles triangle. Is that even remotely reasonable? Why don't I just try to draw a triangle? What? It's a pretty bad triangle. Again. Okay. So given an isosceles triangle, let's make it a little bit wider. Of this form, so let's label some stuff. So this side is the same as this side, it's isosceles, and let's label it ABC like this. So given an isosceles triangle of this format, the median altitude and angle bisector to the base AB all coincide. They're all the same as the perpendicular bisector of the base. The perpendicular bisector to AB. Okay, so these are three fundamental constructions: the median, the altitude, and the angle bisector. They're all the same as the perpendicular bisector in this case. So I think it's worthwhile drawing a picture of this so that we really understand what I'm trying to say. So let's take this. Oh my goodness. Let's draw a few copies of it. Okay, so what do we have? We've got four lines, basically. What am I doing here? Move it down a little bit. So we've got four lines. Now let's go through each of them just to make sure we really understand. So we've got the median. So the median will be where we took the midpoint here, M, and I draw the straight line from M to C. Okay, that's the median, of course. That is equal to that. And then what have we got the altitude? Well, the altitude is where we drop a line straight down from C, which is at 90 degrees, like that. We'll call this H at the bottom. Then we've got the angle bisector, which cuts this angle at the top directly in half. So this here and this here are the same. I'll call them 1, 1. And finally, we've got the good old perpendicular bisector. And the perpendicular bisector, do it in purple. What does it do? Well, it starts at the median, of course, and it's at 90 degrees. So I'll do dot, dot, dot. All right, so this is at 90 degrees. This and this are the same. Okay, so we need to show basically all of these lines line up. In particular, we really want to show that, well, they're all exactly the same, and we want to show that the perpendicular bisector is going to cross through the point C. That's kind of the main thing here. So let's think about this carefully. I think we should start with this triangle, let's say. So proof. So let's start with this guy. All right, so if I want to show this matches up with things like the altitude or the angle bisector, I need to kind of work stuff out about angles. Okay, so let's label some angles in this picture. So let's have this as 1, this is 2, let's have this as 3, and this is 4. Okay, so standard procedure, right? What we really want to do is want to match things up. And to match things up, we need to find congruent triangles. So let's try and show that this triangle here and this triangle here are congruent to each other. I think that's a good plan. So to do this, what do we need? Well, let's go through the usual procedure of matching up sides and angles and things like that. So first of all, by hypothesis, AC is equal to BC. Okay, that's the statement that that length there and that length there are the same. Okay, what else do I know? Well, I know I'm an isosceles triangle, so this implies that the two angles at A and B are the same. So the angle at A must be equal to the angle at B. So this was last week's work. And finally, well, by construction, AM is equal to MB, right? Because we're choosing the midpoint here. So this is by construction. Construction because we are the ones writing down the median. The hypothesis really is we're starting with, we could say hypothesis here too, but I kind of like the term construction. Okay, so what does this tell me? At this point, the side angle side criterion guarantees that the triangle AMC is equal to the triangle BMC. Oh, it's congruent, sorry. Got to be very careful. It's congruent to BMC. What does that mean? Well, if we match up corresponding angles, lengths, everything matches. So in particular, we know immediately that angle 1 must be equal to angle 2. Okay, so what does that mean? Well, that would guarantee that CM is the angle bisector. So it would correspond to this situation up here. Okay, so we've shown that L is equal to M and the blue and the red line match up. What else do we know? Well, the same thing is true for C and or 3 and 4. But they're supplementary angles, remember, right? They form a linear pair if you want. So these guys are supplementary. So what does that guarantee? Well, if they're both the same, it guarantees they're both equal to 90. Well, if they're both equal to 90 degrees, what does that tell you? Well, it tells you that CM is both in altitude and now it's an angle bisector. Or should I say perpendicular bisector? Awesome. So everything matches up, right? We've shown that all four of these have to be exactly the same. In particular, we've shown that this guy up here has to pass through C. Not that my picture does a very good job of it. Okay, so that's proof. Very nice. Pretty elegant proof, I think, right? All right, what next? Well, we want to think about how to determine if, well, some of the properties of angle bisectors in general. Perpendicular bisectors. So here's a really useful theorem, which is going to allow us to prove some pretty solid results. So any point, let's say x, in the perpendicular bisector of a line segment AB has the property that the distance is the same from x to A and x to B. So it's equidistant from A and B. Okay, so let's prove this. So let's take a line segment, A and B, and let's draw the perpendicular bisector. Perpendicular bisector, right in there. Standard stuff, so you're at M here. These two lengths are exactly the same. What are we thinking? Well, we're thinking basically of some x on this line, and we're trying to show basically that if that's my x, these two lengths are the same, which I think is kind of obvious, but we want to really prove it carefully. So the aim, of course, is to show AX is equal to BX, if you want to write it like that. There are several ways to do this, but first of all, let's divide this into two cases, because the way I've drawn it, so this kind of screams some sort of congruent triangle relationship. If we're trying to show two sides are equal, these two lengths are equal, it would make sense to show that and that are congruent to each other. Now, before we say anything though, the way I've drawn the picture is a little bit misleading of the completely general case, because for example, x could be at that position there, it could actually be on the line segment, and then you wouldn't really get a triangle. So it's kind of worthwhile dividing things into two cases. So case one is where x is equal to m. So in this case, ax is equal to am, well that's equal to bm by definition of the median, or the midpoint, and this is equal to bx. Tick. Very good. So that's kind of a silly case almost, but we do need to include it. So case 2, x not equal to m. So now we're going to have to do actual congruent trial business. So let's first of all observe that am is equal to mb. Okay, so this is the hypothesis really, because we're starting with a perpendicular bisector. Again, the angles at M, so AMX is equal to the angle BMX. Again, they're both equal to 90 degrees. Again, that's a hypothesis because it's the perpendicular bisector. And finally, XM, this side here, is shared by these two triangles. So XM is equal to XM, shared side. So what does this tell you? Well, now this tells you by your SAS criterion that the triangles are the same, or congruent, sorry. So not the angles, but the triangles are congruent. And the moment that happens, we can match up sides. This guarantees that AX is equal to BX. Proof. Neat. Okay, so it's a cool result, right? Nice proof, something similar to what we've seen a lot before. It's worth pointing out that this is kind of, in some sense, an if and only if condition. What I mean by that is the following. So this works in reverse. This works in reverse. Namely, if I have a point, so if X has the property that the distance between A and X and B and X are equal, this guarantees that it's on the perpendicular bisector. So this X lies on, let's say, SAB. That's the perpendicular bisector. Okay. So it's basically this picture again, right? So if you have a situation where the two distances here are the same, well, then it has to lie on that red line. Nice and simple. So this is SAB. So it's an if and only if condition. So a point is equidistant between A and B if and only if it lies on the perpendicular bisector. Sweet. So let's now do the following. So I think I should get you to do an example. So go to your workbook and do example 121, question 3. So pause the video and try that. Okay, so this question, what have we got? We've got two triangles stuck together, don't we? So we've got something like a kite almost. Something along these lines, don't we? Not too bad. Okay, so we've got A and B, we've got M and N. And we're being told that these triangles are congruent to each other. Okay, so the triangle AMN is congruent to the triangle BMN. So this guarantees what? Well, it guarantees the sides match up. So AM is equal to BM. So that's equal to that. And AN is equal to BN. So that is equal to that. Okay, so what does this tell you? This tells you, well, first of all, by our previous result up here, M and N are on the perpendicular bisector of AB. Okay? But there's only one line. Well, for any two distinct points, there's only one line which passes through them, right? This has to be the unique line passing through or containing N and M. There's only one line containing two distinct points. So that means what? That means this guy here must be the perpendicular bisector. And that's pretty obvious, isn't it, right? Because if you draw this line, visibly it's at right angles there and it cuts it in half. Okay, so neat. So finally, let's do a kind of an interesting theorem, which is a consequence of this essentially. So theorem. In a triangle ABC, the perpendicular bisectors to all three sides, so to AB, BC, and AC, all intersect at one point. It's a really cool geometric fact. It's not completely obvious at all, right? It's nice that it happens, but proving it cold without the build-up we've done would be quite difficult. So proof. The proof's really cool, I really like it. So let's take a triangle. Nice, and we'll call this side A, well this vertex A, this vertex C. Okay, so what are we going to do? Well, let's draw some perpendicular bisectors, shall we? So let's draw SAB, like this. Okay, so we'll have SAB here. And let's draw SBC. So SBC looks kind of like that. Roughly, maybe something like that. That's a bit better. Okay, so this is SBC. Okay, so they've got to cross each other. Let's say they cross each other at a point. Let's call the point O. Okay, so we'll call this point 0 where they cross. Right, so what do we know? This point O is in the intersection of these two. So first of all, O is in SAB. Okay, so what does that mean? That means the distance from O to A is equal to the distance from O to B. So that length there and that length there have to be equal to each other. But it's similarly on BC. So that means it has to be the same distance between B and between C. So that means the distance between B and the distance between C must be the same. It's got to be the same. So what does this tell you? Well, putting these things together, this implies that OA must be equal to OC. That length there and that length there must be the same. So the distance between O and A and C is the same. So that tells you O must be in the perpendicular bisector of AC. We're done. So that means if I was to draw in the perpendicular bisector, it would have to cross this point. I think that's a really cool proof, right? Because it's not completely obvious. I mean, it feels very neat geometrically, it happens, but why is it completely guaranteed? And this is the reason, essentially. So it's all relying on this fact that if a point is equidistant between 2 points, it has to lie on the perpendicular bisector. That's exactly what we're doing here. Okay, guys, it's a good place to stop. Enjoy your week.